Hi, I'm Chandrima Chatterjee. I'm a lecturer in the science cluster at SUTD. Today, I'm going to be giving you a video lesson on the photoelectric effect. At the end of the lesson, you will get the opportunity to answer a short quiz to test your understanding of the photoelectric effect. Let me explain to you what is the photoelectric effect. If you take a piece of metal and you shine light on it, electrons can get ejected from the surface of the metal, and those electrons will have a certain amount of kinetic energy. In fact, the modern day instruments will allow you to measure the kinetic energy of the ejected electron. Let's try to analyze the effect a little bit further. We are now going to observe how, by adjusting certain properties of light, we can influence the ejection of electrons. We can use a simple circuit as shown in this figure. So there are two metal plates which are enclosed in a vacuum tube. One of the metal plates is exposed to a light source and is called the emitter. As light shines on the emitter, electrons get ejected from the surface, and these electrons travel towards the other metal plate called the collector. Now the electrons start flowing in the circuit, as a result of which there is a current generated across the circuit. This is called the photocurrent, and it is measured by an ammeter. Now let's say we shine red light on the emitter plate. No photocurrent was observed. So our intuitive feeling is that if we increase the intensity of the light, meaning making it brighter, we should be able to eject more electrons and therefore be able to detect a photocurrent. But here's the interesting thing. No photocurrent was observed even with the more intense or the brighter red light. But as soon as the red light was replaced with the blue light, a photocurrent was detected. Another interesting observation is that as soon as the light source is switched off, there is no photocurrent in the circuit. So what do these observations suggest about the nature of light? In 1905, Albert Einstein extended Planck's quantum theory to explain the photoelectric effect. He suggested that light is made up of discrete packets of energy called the photons, and the energy of each photon is given by h nu, where h is the Planck's constant and nu is the frequency of the light. This suggests that the energy of the photon is dependent on the frequency rather than the intensity of light. However, if the frequency is too low, there is a possibility of no electrons being ejected from the surface of the metal, no matter how intense the light is. This means that there is a threshold frequency called nu naught, below which no electrons can be ejected from the surface of the metal. So the question is, why is there a threshold frequency? Remember that there is an electrostatic force of attraction between the electrons and the nuclei in the metal. This is why the incident light must have enough energy to be able to pull out the electron from the surface of the metal. In other words, light needs to overcome a threshold energy, which is also called the work function of the metal. And this work function is given by h nu naught, and it is different for different metals. If the photon has more energy than required, the remaining energy is observed as the kinetic energy of the ejected electron. This means that the energy of the incident photon is partitioned into the work function of the metal and the kinetic energy of electrons. So if we now make a plot of kinetic energy as a function of incident frequency, this is how it's going to look like. It is quite obvious from this graph that below the threshold frequency nu naught, there will be no ejection of electrons. Before we conclude this tutorial, there is one last thing that needs to be addressed. The question is, why was no photocurrent observed even with the more intense red light? In order to answer this question, we need to understand what do we mean by light intensity. Now, the intensity of light is defined as the number of photons that are delivered per unit time. So if you're increasing the intensity of light, you're actually increasing the number of photons that are delivered to the metal. You're not changing the energy of the photons. However, if you're changing the wavelength of light, keeping the same intensity, you're actually changing the energy of each photon. However, the number of photons that are delivered still remains the same. This concludes our video lesson on the photoelectric effect. You may now proceed to answer quiz 1 posted on the e-dimension. Thanks for watching the video and best of luck.